Okay, so as everyone here probably knows and is well aware, hopefully, exam three opens tomorrow on Tuesday, and it will be due by the end of Wednesday. So still, you can take it either day. Just again, like always, it uses Honor Lock. So make sure your browser's up to date. We should be good after the first two exams. Um, you can use that cheat sheet on there. The instructions are in the announcement. So the only real stipulations is it needs to be on a physical piece of paper. It needs to be handwritten. Some people did ask, so I want to mention it here too, that they can do handwriting on like a tablet and then save it and print it out. That's fine, as long because that's still technically handwritten as long as it's on that piece of paper. And just remember to show both sides of the paper for about maybe 2, 3 seconds to the camera, just so you can get a glimpse of kind of what's on there. And then remember, you can put anything written you want. You can put the equations, you can put definitions, you can put your notes. Um, I highly recommend putting the equations on there so you don't have to memorize all of them because you will have to do several calculations on the exam itself. All right, are there any questions about the course in general, kind of, or exam three, before we get into the content?
Hi, my question is on doubling time. Um, I know we went over it, I feel like we went over it really briefly and we just kind of talked about the concept of it. And one of the sections, I can't remember if it was T10 or 11, had all the formulas on there about it. Do we need to know those formulas, or are we going to be focusing more on the rule of 70?
You'll have to know the doubling time conceptually, so knowing kind of what if you see the formula or how you can accelerate or decelerate doubling time would be good to know. What the rule of 70 is, it would be decent to know because it was in one of the videos. But you won't do any calculations of doubling time. That I can confirm.
Okay, thank you.
Yeah, no problem. Okay. I'm going to go ahead and share my screen then. Everybody see my calc okay?
Yes.
Okay, cool. So it starts off talking about fluctuating age structure. So this is kind of building on the life tables and population growth and decline that we've covered in the first three modules for module three in these last two. And right here is this kind of using real data with fish to show an example of how you might kind of see anomalies, or at least what appear to be anomalies in a population where you might see kind of random jumps. What was their explanation here? So they were capturing fish and looking at different age classes over time and looking at, just different, the numbers kind of or percentages in the different age classes. And as we see in 1946, it seems pretty even, but in 1947, there's this big jump in age class three. What did they kind of attribute that to?
Higher reproduction during that period.
Yeah, well, they're 3-year-olds, so why didn't, in the previous year, why wasn't age two right here really high? Because we're not adding it. These are 2-year-olds that survived to be 3-year-olds from 46 to 47. So you're not adding new 3-year-olds to the population, right?
This whole concept didn't make much sense to me unless you had an isolated population, because the species is made up of a variety of different ages and it should affect all of the ages equally unless they're isolated.
I agree that you would see it a lot cleaner if you had an isolated population, but the idea here is not every age class is going to be have equal consequences or results, right? And the reason that there's not even like an age one or an newborn age simply here is because their traps that they used were inefficient. They weren't able to catch newborns or 1-year-olds in their nets, so they don't even really show up until age 2, and they still think that they underrepresented age 2 in 1946 because of their small size. And then all of a sudden, when they turned 3 years old, we get this jump in 1947 because now they can actually capture them. So what they're showing is they actually missed the birth boom of this cohort right here. They didn't adequately capture it for the newborn, the 1 year old, or even the 2 year old. They really didn't show up on the radar until they were 3 years old and of size to be caught in their nets. Because then when they turned 4, they were high. When they were 5, they were high. And when they were 6, they started to kind of have a die off. So it was just to kind of show that you can have differences in age categories. Like you can have like 1 year, you have a really good reproductive year, low predation year. So you have a really big birth year. But depending on the methods they use for sampling, they might not capture that adequately until they're in later life stages here, really until they were 3 years old. And it doesn't go into a ton of detail, I agree. So it kind of glosses over that idea, just showing how age classes can fluctuate across age classes and they're not always equal. For whatever reason, again, this had, a boom for, this cohort that maintained after so many years. But the other cohorts weren't nearly as plentiful. Okay, and then they get into modeling age structure by introducing, bringing up previous concepts of geometric growth, the net reproductive rate, survivorship, fecundity, and then they introduce this concept of matrix. And you can build these matrices to model population growth. And it kind of breaks it down by different age categories. And it pulls information from the life tables that we've seen already, right? So we need to know age, the population numbers per age category, the survival rate from 1 year to the next. They have survivorship on here, and then they have fecundity, which is going to be the reproductive success per cohort for a given year. And then they put them into these, what they call the matrices here, where you have fecundity on the top row. So this is all of our B of X values up here. And you have the survival rate, the S of X values that go on a diagonal here, and the rest of the values are 0. And what we can use these matrix tables for is estimates for how many newborns are we going to have for the next year, how many are we going to have surviving in each age category for the next year, and what's going to be the estimate for the population number for the next year. And you can do that repeatedly and get population estimates over a long period of time using these numbers. And we'll go through the activities together and the calculations, and I'll show you the strategy that I implement, which largely comes from that video that I sent a link to last week in one of the announcements. So this kind of just briefly introduces it here, where how do we predict how many newborns we get? Well, we have to take each n value for that age class, right? So year 0, we have newborns, 1-year-olds, N2 is 2-year-olds, 3-year-olds, and 4-year-olds, and they all have an associated fecundity value. And we multiply each one, so we get that out of this class. So at age 0, you have 1,000 individuals, and their fecundity is 0. So 1,000 times 0 is 0. But they actually don't use that life table. They give you the numbers here. Okay, so these are where these numbers come from, right? So they say we have these different numbers, 50, 40, 30, 20, 10, and 3, that corresponds with ages 0, 1, 2, 3, and 4, and 5. And they give us the fecundities of 0, 0, 2, and 4.5, and 1. Okay, so this is where the multiplication comes in with the n of 0. That's going to be, we have 50 of them. Their fecundity is 0. So that's where they get 50 times 0, right? So the newborns, not surprisingly, aren't going to produce any offspring. The 1-year-olds also don't, they have a fecundity of 0, so they don't reproduce until age 2. So that's where you get 30 times 2. So age 1, 2, and then age 3 is 30. So 30 times 2, 20 times the 4.5, 10 times 1.0, and then we add these all together, and then for the next year, it's going to be a total of 160 individual new babies for the next generation. And then they talk about how we plug these numbers into the matrix by adding new columns, because what we're given this information again, all the fecundities, the B values, all the survival rate, the S values, and we're given the population size at time T. So population of newborns, 1-year-olds, 2-year-olds, 3-year-olds, and 4-year-olds. They made a note that they don't add the 5-year-olds in because they don't survive, so they're not going to even be considered for the next population because they all die off. And what we're solving for is the newborns, the new 1-year-olds, the 2-year-olds, 3-year-olds, and 4-year-olds. That's time plus 1. So that could be 1 year, 1 month, whatever time interval it is, it's plus 1. And that'll be the new numbers for each age category in that following generation. And they show how they put all the math in here. So we already did the top row above. So N of 0, B of 0. And then it's the same idea with these survival rates, right? N of 0, S of 0, N of 1, S of 1, N2, S2, and N3, S3. And then they're trying to solve for this. And then here's, again, we've already done this top row together. And then this is all the survivals. So this is the total population of 1-year-olds times 0.5, 2-year-olds, 3-year-olds, 4-year-olds. And we know we already solved 160 newborns. And then of the previous newborns that are now 1-year-olds in the next year, 25 of them survived, right? So you had 51-year-olds at a 50% survival. And now there's only half of them, right? 25, 32, 27, and 4. So they do it one way, which I think is not the easiest way to follow. I'll show you my notes in a second when we get into these activities, how I set it up, and you get the same values, but it just looks a little different. Okay, this first activity is actually, they just break it down, right? All the B values go in the top. We've already talked about that. So this is our fecundity values in the top. And then the S of X values are the ones that go diagonally.
I got a quick question for you while you're dragging that stuff around.
Sure.
So you're mentioning that you have kind of a different way to kind of solve this problem set, right?
Yes.
When it comes to seeing like a chart like this on the test, is it going to look like what we're seeing in cog books? And it's up to us just to generate like our own, how we figure it out is how we figure it out.
Yes, that's the good
Okay.
way to put it. Yeah, you can
Okay.
use the cogbooks method and that'll work perfectly fine. You
Mhm.
can use the method that I got from that video where they call them Leslie's matrix models. And it's just, you'll see it in, like I said, in a few seconds, the setup for it. Because what you're going to see on the exam is going to look a lot like this activity right here. You're going to be
Mhm.
given a matrix table. You're going to be given the population for each age category, and then you're going to be asked questions like you might see a multiple choice question that says, given this information, how many 3-year-olds would you expect in population at time t plus 1? And now what I would recommend is, well, not that I necessarily recommend one over the other, but an alternative way to do it is when you're given, let me zoom in a little bit. All right, you're given this information right here, right?
Mhm.
This is the activity. These are the values. We know the top row, the diagonal. And what I did is I said, first, let's fill in the matrix table, right? So you're given, these are not filled in, but we're given the information in the question so we can fill it in at time t. And now we want to solve for this, and we want to look at 3-year-olds. So we're going to end up finding, so newborns, 1-year-olds, 2-year-olds, 3-year-olds. For the first question, this is the box that we want to solve. I would recommend solving all of it first and then pulling out the information rather than trying to jump just to 3-year-olds. You find out how many newborns you have, how many 1-year-olds, 2-year-olds, 3-year-olds, 4-year-olds survive. And I like the idea of creating a new life table. And you like kind of, I fill it in this way, right? So you have age at each age bracket, you have N of X, you have the fecundity values you can put in, the survival rate values. You can calculate, I call it new babies. So this is new babies by age category, and then the survival of each of these right here. So again, it's using the same information, but then the first thing that I would do is just start calculating the amount of new births, right?
Yep.
Yeah, is there a question?
Yeah, and on that table that's half seen there, what would N2 be? What are you multiplying? You lost me.
So N2 is right here. It's
Yeah.
N2 is 35 individuals. And that we would see it would be given to us right here in words, right? They gave us N2 equals 35. When we go back to the problem, and I plugged it in to a table, like I'm recreating a new life table for the following generation is what the way I like to approach this.
Okay. Now, how are you getting new babies there? What was my question on that?
Okay, yeah. So this is the formula right here. So to get new births, you take the N value, so N of X, so we could take N0, 122, and we know that we have all the B of X, the birth rate or fecundity values, and you multiply these two columns together. So N of X times B of X for the newborns is 122 times 0 is 0. So the newborns had no new offspring. The 1-year-olds, that N of X is a 101. Their birth rate is also 0. So again, they're gonna, N1 times B1 equals 101 times 0 is 0. And then N2 is 35, but now the 2-year-olds do have a birth rate. Like they have a fecundity value that's not 0, so they will give birth. And we take N2, which is the 35, and we multiply it by B2, which is now 0.2, and that gives us 7. So the current year 2-year-olds are going to give birth to 7 individuals. And we can do the same thing for 3-year-olds. That's N3 times B3. So these two columns, 26 times 0.4 is 10.4. I like to leave the numbers as a decimal personally, just as I'm going, add them up at the end, and then choose to do the rounding if you want. If you're off by, a decimal on the exam, I'm not, that's not going to count against you. If this is a short answer question with multiple parts, and you say 39.6 and, the answer key says 40, as long as the math is correct, you're going to get full credit for that. Because some people make the argument you can't have 0.6 of an individual, true statement. So if you want to round it to 40 or round it down to the nearest whole number of 39, either way is okay. So we do that for each age category, right? And then we can sum them up. 0 plus 0 plus 7 plus 10.4 plus 12.6 plus 9.6 gives us 39.6 or rounded to 40, either way. So we know that in T plus 1, it's going to be the newborns of that year, the total is 40. So if we remake this this is N of X, so say this is N of 0, it's 122, and N of T plus 1, the newborns for the next year, this value here, that would change to 40. And you can create multiple columns and calculate this year after year, assuming the same birth rate and the same survival rate. And we do the same thing for survival, right? So we know we have 122 newborns for the first year. How many of those survive? Their survival rate is 94.6%. So we take N of 0 and, sorry, wrong column, N of 0 and S of 0. So the 122 times 0.946. So out of the 122, 115.4 will survive. And we do the same thing. We take our N1 value again, and now we use our survival rate value. So the 1-year-olds, 101 of them survive at a 98.5% or 0.985 survival rate. So out of the 101, 99.485 survive. Do the same thing here. We have our N2, S2 value that come from the columns. We have 34 survive. For 3-year-olds, we have 25 survive. And for 4-year-olds, we have 8.4 survive. And 5-year-olds, their survival rate is 0. They don't make it to age 6 in this population. So it's, 6 times 0 is going to be 0. And what we can do then is we can say we started with 304. We added 40 new babies. And out of that 304, 283 survived. So we note some information here, right? Like we already said, we start with 304, 40 new babies, 283 survive. We can also say 304 minus 283, 21 adults died. Because they might ask, what was the total death count of that year? The total death count would be 21. Okay, so now we filled in our life table. On the bottom, we have, our information that I bolded, noted here. And then we can also say what the new population is, right? So we have 283 surviving adults from up here, plus the 40 new babies that we counted up here. The new population is 323. So we know that this population has increased from year 1 to year 2 because it went from 304 to 323. And then this is the video that I was commenting on where this method kind of comes from. The link is here, but the link is also in the announcement. So now what we can do is we can go to the questions, and having all this information, we can just pull the answers very easily from our new life table to answer those questions. Rather than answering them one by one, doing the math, we can do all the math up front and then see what they're asking for. So what that looks like is, all right. So it says, how many 3-year-olds would you expect in the population at time t plus 1? Another way to word that question is, how many 2-year-olds from the first population survived to become 3-year-olds? And that simply is our N2, S2. So how many 2-year-olds are there? What's their survival rate? There were 35 that survived at 98.5%. And that gets us our answer of 34. And that comes from right here, our 2-year-olds, and their survival is 34.44. And the second question says, how many newborns, 0-year-olds, would you expect in the population at t plus 1? So this, we had to calculate all the births to get this, right? Because another way to say it is, how many new total babies are there? And that comes from all of our new baby calculations, right? 0 plus 0 plus 7 plus 10 plus 12 plus 9, 39.6 or 40. And that's where that value of 40 comes from. Question 3, this says, how many of the newborns expected at time t plus 1 would be produced by individuals that are 3 years old at time t? To me, that's kind of a mouthful. A simpler way of asking that is, how many babies were made by the original 3-year-olds? Right? So we take our N3, our number of 3-year-olds, times their fecundity, that's that 26 times 0.4 equals 10.4 or 10. And, you could do the math individually down here, or you could, have your table where we pull it from. This comes from this box right here. Okay. So are there any questions on the matrices? Like I said, you can make a new life table like this for me personally, it just organizes it better where I can see where everything's coming from. So I'm not stressed out when I'm answering the questions and thinking, I'm pulling a number from here and a number from here. This just lays them all out, and you can pull from it when you're done and answer pretty much any question from it. But again, either way works. For the exam, when it says show your work, you don't necessarily have to show the entire table if you don't want to. You can, it won't hurt, but you do need to show at minimum which equation that you're using to get your answer. So that's the minimum of the amount of work you'll have to show on the exam. If it's a multiple choice question or true false, you won't have to show work. It will specify in the question, which will be one of the short answer questions if you need to show work or not.
Are you doing your booklet? Let me see.
Okay. If there are any more questions on the activity, the rest of this module is really just a series of videos. We already mentioned, the rule of 70 is mentioned in there. So understanding the general concepts of the video is going to be important. He shows some ways to calculate population growth. Some of the equations aren't covered in cogbooks, so none of the equations that are introduced, if they're not in cogbooks, you're not going to be responsible for doing the math of them in these series of videos. It's just kind of another way to talk about birth rates, death rates, and changes in population fluctuations. In the case, we're not gonna watch these videos together. You can do that on our own time. But they did have a few questions in there. One of the questions they asked was a true or false question. It said, a growing population will have greater proportion of older people than younger people. True or false? Why? Let's talk about it a little bit here. So it's saying a growing population will have a greater proportion of older people than younger people. Is that true or false?
False.
Yes, I agree. It's false. Why is it false?
Because it's oh, sorry. As the younger people or as the older people are aging out, it's the younger people that are ones doing most of the reproducing and add new members to the population. And so you'll see over time that those younger members, as they're reproducing, they're beginning to grow older, and like that's where you kind of see like that diamond effect, or the pyramid kind of becomes less of a pyramid and more as they're beginning to age, and then the newborns and stuff are beginning to age as well. So,
Well, you're definitely right on track. Going to the pyramids that we saw, like with the different age categories in the previous module, is exactly where we should be thinking. But you said it becomes less of a pyramid. What do you mean by that?
like instead of there being so many, um, instead of the the amount of people at the younger age being so much greater than the people at the older age, like that's going to start to kind of even out over time as like you'll kind of see that move up, right?
Um, I would disagree. I would argue that it would become more of a pyramid because this is a growing population. In one
Oh yeah, okay,
sentence,
I see what you're saying.
the base of that pyramid is going to get wider and wider,
Hmm.
indicating that it's growing, right? I agree with you said, right? You're going to have older generations are going to be less in number, and younger generations are going to be greater in number, and that would make it be more of a wider base. The wider the base, the more the population is growing, right? Because that means that the older generation is having more offspring. That offspring is having even more offspring each generation is more than replacing itself, and that's causing the population to grow. So each younger age bracket is going to get wider and wider and wider as long as it continues to grow. If it evens out, that means that they're just replacing themselves and the population is going to become stable. If it narrows, it means they're less than replacing themselves and the population is going to decrease. So again, it'd be a lot easier to have visuals with this question, like from the video, but okay. Then the second question that the video pulls out is, it says, it's another true or false question, and it says, human populations experience density dependence but have no carrying capacity.
False.
False.
Yes, I would agree. False again, right?
So,
And it's a two-part question. You know, which part of the statement is false? Is it both of it about the density dependence and carrying capacity, or is it singular about the density dependence or the carrying capacity?
Carrying capacity kept growing because of technological advances, medical advances, etc. So it wasn't leveling off like it's supposed to. It kept exponentially going up.
Yeah, so the first part, populations do experience density dependence, but humans do have, it says, but there's no carrying capacity, and that part is the false part, right? It appears that humans in most places have not necessarily reached their carrying capacity, but every species, every population does have a carrying capacity. It might be growing exponentially for a time because it's quite a bit below its carrying capacity. And as you mentioned, human technology and food and shipping of food and locally or not locally, non-locally, I should say, that we talked about in the last office hours, it can raise the carrying capacity, right? So medicine is a great example. People don't die, that wear glasses like myself. I would have a hard time if I didn't have eyeglasses and I needed to hunt, right? I wouldn't be able to see as well, but multiple forms of technology have helped me. I have eyeglasses that help me see, keep me safe. I can see, potential predators better. But also I don't really hunt for my food. I can go and buy food that has been hunted or raised based on other technologies. So that subsidizes me, that I don't have to have those hunting skills necessarily. And we can, again, that's how we can raise our carrying capacity as humans. Okay, are there any other questions from T12? Okay, if not, cool. If they come up later, again, obviously feel free to email me or message me. And we can talk about T13. It focuses on metapopulations is a big theme here, but also that, in the title, population dynamics occur over space and as well as time. So we've talked about a lot in the last few modules how populations change over time, right? Estimating population in 1 year and estimating the new population numbers in another year or the following years and building on that. But that's part of what's not equal that we talked about is the age structure, right? They have different fecundity rates, they have different survival rates, but also we're going to have differences in the same species across populations, especially when the habitats are different and especially when habitats are fragmented, right? We've talked about fragmented habitats. We know what those are. That's where you had, like, say, for example, you had a large forest. There was some natural disasters or even humans came in and cut up some of the forest. So it fragmented the big, large, continuous forest into smaller patches that are separated from each other. And you can cause differences in the quality of those patches, right? So we talked about, bigger patches in closer proximity are better for biodiversity. So here, bigger patches, can lead to differences in population structure. So you can have different numbers in these different habitat fragments. So one of the fragments might be, grassland or forest, and another fragment might be swamp area. So if you have bird populations in both, they're gonna have different resources in both habitats. So you might have, them do better in one habitat than in another habitat. Okay, and then they introduced the concept here of metapopulations, which by definition is the subpopulations of an original population when individuals are able to move between patches. So it kind of takes that one big population and breaks them up into different patches of habitat, but they can still generally move and be, across these patches. And then they talk about there's 3 types of metapopulation models. I don't know why they didn't bold them here, but there are 3. There's the basic metapopulation model, and that one is really simple, hence the name, right? It assumes that all the habitat patches are of equal quality and that the habitat matrix between the patches is inhospitable. So what it means by habitat matrix, say the patches are the water in this environment, the matrix would be the land that is connecting the water. So it's going to assume that all the water patches are identical, but if you looked at this pond and this pond, just based on their difference in size, I think you could make, they're going to have a different amount of resources. This model is rarely correct, but they started with just a very basic model, and they also assume that, organisms in this resource cannot function in the matrix being the land here. So for them to go from one patch to the next is very difficult. They can only be in the matrix. It's inhospitable, so they can only pass through it very quickly, if at all. All right, the second one is the source sink metapopulation model. So this builds on the basic model, but it incorporates the fact that habitat patches do differ in quality. And in fact, they introduce sources and sinks right here. They say that the high quality patches are known as the sources. So that's where there's a lot of reproduction and populations can grow in these source populations. So they produce offspring in high numbers. And so they don't eat themselves out of home. A lot of the organisms that when they reach their carrying capacity, they will migrate elsewhere and go to some of these low quality patches known as the sink patches. They can usually sustain, like, if they make it there as adults, they can live out their adulthood, but it might be very difficult to reproduce. So if that source population were to disappear, that sink population would sustain maybe for a few years or the lifespan of these organisms. They might reproduce a little bit, but you would generally see a decline and maybe even eventually a local extinction in these sink patches because they're low quality patches. So having sources feeding the sinks patches keep those sink populations sustaining. So you can kind of think of it as, like, I think they're partially called a source sink because if you have, say you have a sink and then there's a source of water you pour into that sink, you can fill the sink all the way up. But if you turn that source off, that water in that sink is going to slowly drain and empty. And as long as you keep kind of like a steady trickle of water in there, you can maintain a stable population. So and that's the analogy that they're going with the source and sink. And then the third model is the landscape metapopulation model. So this one is the most realistic because it acknowledges that both patches and the habitat matrix can vary in quality. So again, these patches are going to be different, but this matrix connecting them could be different than the matrix in here. And if we look at the image, that makes logical sense, right? You have a different habitat patch here than you do in here. So maybe you have a swamp versus a forest. Those are your 2 types of matrix connecting these different bodies of water. And obviously for, say, a salamander, a swamp might be a lot easier and a higher quality matrix that salamander can spend more time in. Maybe it's good foraging in here. So maybe there's more food resources versus in a forest. Salamander can live, but it might get a little dry in parts where it can't spend as much time in there and it needs to return to one of the higher quality habitat patches, and it can't spend as much time in the matrix patch. Okay, and then they get into, very briefly, they talk about how modeling of metapopulation dynamics occurs. This calculation, there's no activities, there's no practice with it, there's really no example. So there's going to be no calculations using this on the exam. But understanding the pieces conceptually is fair game for the exam, right? So with P, the point of this equation is to estimate some fraction of occupied patches. So the patches is the P. The little symbol above it indicates that it's an estimate. And this equation is pretty basic. It's just 1 minus E over C. And E is a fixed probability of each patch becoming unoccupied. So maybe a subpopulation going extinct. So E for extinction. And then C is a fixed probability that each unoccupied patch could be colonized. So C for colonization. And it's just, 1 minus extinction probability over colonization probability. So if the extinction probability is greater than the colonization, you're going to have a lower probability of the patches being filled. If the colonization is greater than extinction, you're going to have a higher probability of the patches being filled. And that's about as in depth as we need to understand this metapopulation modeling dynamics equation. But what does it measure? What do the parameters represent? And how do you make the probability of colonization go up or down, or filled patches go up or down? Okay. And then this part, this is just kind of like a real world example again, where they did a study. They found there were 1,600 presumably suitable meadows on these different islands. But when they went out and measured, they found that only 12 to 39% of those meadows or these patches were occupied in any given year. So they were a little confused why the numbers were so low and they weren't occupying all the patches, or even a higher number of patches per se, not necessarily over them. So they actually studied this for a 9-year period. And they observed, what did it say? They observed more than 100 of the occupied patches experienced extinction each year. So even though that they were potentially suitable, there were local extinctions, and they didn't necessarily figure out all the the parameters or variables of why. Some of it was competition, so maybe the food resources weren't as high. Some of it was predation levels. Some of it was they just didn't reproduce enough, so maybe they didn't leave their source population and venture out into some of these suitable habitats. If they transplanted them, they could survive out there, but there's just kind of a number of reasons why they're not occupying every single possible patch that is presumably suitable for them in this butterfly species. Okay, and then this is just another kind of real world example using numbers to show. So maybe presumably this is kind of the source right here. All these black circles or shapes represent a subpopulation of this metapopulation of these owls, and the numbers are just how many owls are in that patch. So you have a couple really fruitful, potentially source populations that have a little over, close to 200 or over 200. And as they move away from these sources, the patches are smaller. So not surprising, the numbers in these patches go down. They're also a little bit different in quality, right? Like this one might be the largest and best shaped patch, but it only has 190 compared to this one has 266. And they don't get into the details, but there's something different between these two patches. This might have more nesting sites. It might have more food, possibly. It might have fewer predators that they're able to produce at a higher number. And something too, it might just be the given year, right? They just had a really fruitful year compared to over here. And you might see switches in the future where this one actually has the most, and then this one has the second most. Because there might be something that happens from year to year. But the big idea here is that patches are different, as we've talked about, and they're going to have different numbers. And usually, with the further you move away from a source patch, the numbers kind of go down. It's not perfect because this is 6, this is 60 and 100, but this is also a really small patch compared to these two over here. So And then they introduced the term the rescue effect. And that just by definition, when dispersers supplement a declining subpopulation that is headed towards extinction, right? So having, excess numbers in these larger patches, you might get some young ones that migrate or some weaker ones that get put out competed and pushed off, and they got to move to these other populations, and their movement to them is actually what is maintaining those numbers. If you cut these patches off from the source over time, you might actually see some local extinctions. Okay, and then this one was a pretty short module, so that's really all that I kind of wanted to go over in T13 with the group. Are there any questions about T13, T12, or the exam?
How much detail of the equations, you could fill quite a space on some of these, it looks like. You want to know the formula, you want to know some of the arithmetic, but how much?
I mean, that's a tough question to be honest, because the easy answer is it's up to the student. What I would recommend is if you saw the equation in the activity, I would write the equation on my notes, like the geometric growth model. I would write out the all the parameters, like what the equation, and I would write a short key of what they equal. Because for me, it would be less that I would have to remember. If I see the equation, I can personally, and I know what the parameters are, I don't have to write out necessarily an example because I can see how they're multiplied in the equation and I can do the plug and chug arithmetic.
You're talking that's on our cheat sheet or on the test?
I'm talking that's on the cheat sheet. I guess maybe I misunderstood your question then. I thought you were asking maybe what.
Yeah, how much detail you want on the arithmetic on the test?
Oh, okay. So in the true false multiple choice, you don't have anywhere you can write anything, so you aren't required to show any work there. On the short answer, there's going to be, possibility of a couple questions asking you to do the calculations, and it will specify you need to show your work. So say, for example, it says, how many newborns will there be in year 2? Like what we just practiced. You need to show the equation, the math where you did newborns times their fecundity equals X. 1-year-olds times their fecundity equals B. You need to show those that you calculated each one and that you summed it up. Does that make sense?
Yep.
Okay. Yeah, so for the short answer, when you have to show work, the more work you show, the better it's going to be. Because we need to know where because part of it too, the reason I want to see your work on the short answers is it might be a 3-part question and you got part A, you calculated it incorrectly, which is going to give your answer to part B, and part C likely is also going to be incorrect. However, myself and what I've told the TAs is if you get part A wrong, let's say you did the equation maybe right, you can get partial credit for that. You just did the math wrong. But then we will read your answers for part B and part C. So part B might go, is the population growing or shrinking? If you calculated the new population wrong, you might have got an answer that's higher than the previous year and you said the population is growing. Well, technically that's wrong, but we would give you credit for that because that part B is based on the number in part A. So I want to be able to give as much partial credit as we can. So that's why if we see your work, it's going to help us in grading, give you that credit. If you show no work, we don't know where you went wrong. We can't give you partial credit if you just guessed it was growing, right?
I have a question about the matrix calculations. Um, are we going to be tested on just the current year? Because you were saying like the new babies, you total those up and then you carry that 40 back up, and that's the new NO, correct? Is what you were saying? Or are we going to
Yeah,
have
that
to?
would be the new NO for T+1.
Okay, for T plus one. Are we going to
Yeah.
have to calculate several years ahead, or is it just like, is it going to be current year?
No, you'll be given the information for the current year, and the calculations as far as you would have to go would be for the next year.
Okay.
You
Oh,
can technically do it for like 5 years, but I also understand there's a time limit on the exam. So I'm not going to say, 5 years down the road, make you do it 5 times. If you can show me that you can do it one time for the next year, I believe you can do it for the third year or the fourth year. Like it's a proof of concept that, and it doesn't need, because that would be really time consuming. Spend 30 minutes on one question and you only have 2 hours for the exam. So,
Okay.
or 3 hours, sorry, not 2 hours. No, but that's a good question. And as we saw, the complexity of those questions can range. So also you might be asked a question, how many what is the population of 3-year-olds in the current year? And that's simply just pulling the number from the information you were given and answering it. So there's no math in that particular question.
Okay. I was just wondering if it would pull off a question like how many newborns will be produced by 3-year-olds 2 years from now or something like that.
No, it could be that level. It could say how many newborns were produced by 3-year-olds, right? So
Uh-huh.
you just calculate for 3-year-olds, but it would be in that current year, but it's not going to be like out in year 3 or 4. At
Okay.
most, you're going to be asked about year 2.
Okay. Thanks.
Yeah, it would be year 1 to year 2 or year 0 to year 1. So just a single year from one to the previous is as far as we're going to go. All right, are there any other questions? If not, I think we can go ahead and call it a session. So there wasn't as much in this one, which is okay. But there's still, remember, it's the 5 modules that it covers for the exam. If there's any questions uh, in the next day or so about the exam, please reach out and I can, continue discussing topics with you.
Thank you.
Thank
All
you.
right, no problem. And thank everybody that joined and was able to participate. Have a good night.